China builds the world's longest undersea tunnel. It is understood that to take up the connection between Zhongshan and Ningbo,
China has been digging, drilling, and building underwater in ways that used to sound impossible. And now the world is paying attention, especially American engineers who didn't expect China to push tunnel tech this far, this fast. From massive shield machines to the bold decision to run rail lines straight beneath the sea, China's undersea tunnels aren't just long, they're record-breaking.
A new railway in China is about to send bullet trains straight under the sea. Not a ferry, not another suspension bridge, an underwater tunnel.
The wild part? These mega projects are only getting bigger, deeper, and more ambitious. Ready to see how. Mandarin technology, how China pulls off these undersea giants. China didn't suddenly decide to build tunnels 5 kilometers beneath the ocean for bragging rights. These underwater megastructures are the result of a long strategic push into engineering innovation, what many international experts casually refer to as Mandarin technology. It's not about the language. It's shorthand for China's bold, scaled-up, build it fast and build it smart approach that has redefined modern infrastructure. The secret behind these projects starts with a familiar machine, but taken to a whole new level: the tunnel boring machine, or TBM. China doesn't rely on imported TBMS. They design and manufacture some of the largest, most advanced, and most customized boring machines in the world. Their cutter heads are massive, their pressure balancing systems handle shifting marine soils, and their robotic assists keep human workers out of the riskiest zones. Instead of copying European equipment, China partnered with global engineers, learned everything, then pushed the technology even further. What surprises many American engineers isn't that China builds tunnels, it's how fast they build them. A project that might take 10 years in the US can be finished in half the time in China. That speed comes from extreme specialization, custom-built equipment for each project, and the fact that these tunnels are part of a national strategy rather than isolated infrastructure ideas. China treats tunnels as economic engines, connecting ports, cities, and entire regions, and that mindset fuels massive investment and innovation. One method that stands out is China's large-scale use of immersed tube tunnels. These are giant concrete sections constructed on land, floated out to sea, then carefully sunk and locked together beneath the water. Western countries use this technique too, but China pushes it to greater lengths and depths, using AI-assisted alignment and high-precision positioning systems to ensure each segment fits flawlessly. China also stabilizes the seafloor before building, reinforcing weak sediment with jet grouting, deep soil mixing, or injected concrete. It's like creating an artificial underwater foundation so the tunnel has something reliable to sit on. Add in real-time monitoring sensors, pressure tracking, geotechnical analytics, and redundant safety systems, and you get tunnels designed to survive unpredictable marine forces. American engineers are impressed. They respect China's ability to integrate ventilation, drainage, emergency exits, pressure-resistant linings, and flood protections into one cohesive plan. From day one, U.S. builders often have to work around older infrastructure and long approval timelines. China simply clears the way, funds the project, and executes. The result is a new era of deep-water tunnels that set global benchmarks not only in length, but in technical ambition and construction speed. China still critiques its own methods and learns from each project. But one thing is clear: underwater mega-tunnels are no longer science fiction. They're here, they're functional, and they're reshaping coastal engineering. Then came the projects that showed everyone China wasn't just experimenting, they were executing. And the first real proof of China's tunnel ambitions came from a place most people barely think about: Zhanjiang Bay Undersea Tunnel. Zhanjiang Bay wasn't the loudest project in China's lineup, but it became one of the most revealing. On paper, it seemed like a straightforward transit link, just a few kilometers under a calm-looking bay in Guangdong. But engineers knew better. Beneath the surface were soft seabed layers, unpredictable silt pockets, and shifting geological plates that made the area anything but simple. If China wanted to prove it could build reliable, long undersea tunnels, Zhanjiang was the place to show it. The teams approached the bay like surgeons, mapping every inch of its underwater terrain. Instead of relying only on traditional surveys, they used real-time sonar grids, pressure response monitoring, and automated seabed scanners that updated conditions by the hour. This constant feedback became the backbone of the entire operation. Whenever the seafloor moved, even just a few centimeters, engineers adjusted shield tunneling direction, cutting torque and soil pressure to keep everything stable. It was the kind of precision usually reserved for aerospace projects, not civil engineering. One of the biggest challenges was water intrusion. The deeper the tunnel went, the more the bay pressed in, almost like it was trying to squeeze the machinery out. The solution? A custom-designed slurry shield that balanced inside pressure with the exact weight of the surrounding water and soil. Too much pressure, and the tunnel could bulge. Too little, and water would rush in. Getting this balance right was a constant dance, but China's teams maintained it almost flawlessly. Construction also had to respect the region's marine ecosystem. Instead of dredging large sections, which could destroy habitats, crews minimized seabed disturbance by staging work from carefully placed platforms. Even American observers noted that China was moving toward a more controlled, data-driven tunneling philosophy, something the US had only recently adopted for major projects. But perhaps the most impressive part was the pace. China built the Zhanjiang Bay Undersea Tunnel faster than most nations complete environmental reviews. This wasn't due to cutting corners. It was due to meticulous planning, 24-hour engineering shifts, and a logistical system that delivered materials with almost zero downtime. Every ring segment, bolt, and sealant batch arrived exactly when needed. By the time the tunnel opened, it had proven several things. China could master soft soil undersea tunneling, handle high-pressure environments, and coordinate teams at a scale many countries struggled to match. It wasn't the longest tunnel, nor the deepest, but it was a statement. China wasn't experimenting anymore. It was executing. Next up was a tunnel that forced China to push even harder. If Zhanjiang proved China could build underwater, the Jintang tunnel proved it could do it under pressure, literally, Jintang Undersea Tunnel. The Jintang Undersea Tunnel sits in one of the most unpredictable marine environments on China's east coast. Unlike the calmer waters of Zhanjiang Bay, this region faces strong tidal surges, fast-moving currents, and seabed sediments that behave almost like liquid when disturbed. From the start, engineers knew this project wasn't going to play nice. They were basically digging through a shifting world where the ocean changed its mood every few hours. The tunnel was part of the massive Ningbo-Zhongshan corridor, a plan to connect scattered island cities to mainland China. Jintang Island, which had long relied on ferries and weather-dependent routes, needed a stable link. But building underwater here wasn't just hard. It was something many engineers quietly doubted was even realistic. The seabed was a mess of soft soils, deep layers of clay, and sand that seemed to move like waves beneath the waves. To deal with this, China didn't just pick a machine. They built one. A custom super-large slurry shield was engineered specifically for the Jintang project. This thing looked like a mechanical beast designed for a sci-fi movie. Its cutter head wasn't only strong, it was smart, able to detect pressure differences, soil density changes, and even anomalies like buried boulders. Whenever it sensed something off, it adjusted cutting speed and slurry concentration instantly. It was the engineering version of reflexes, and it needed those reflexes. One of the biggest threats was face collapse. Basically, the tunnel front caving in from pressure imbalance. The slurry shield had to maintain perfect balance between internal and external pressure at all times. Too much pressure, and the tunnel face could blow out, creating massive sinkholes in the water above. Too little, and the ocean would try to punch its way in. Maintaining that razor-thin balance 24/7 became one of the defining challenges of the project. Another problem was the tunnel's path. Unlike some straight, predictable undersea tunnels, Jintang had curves, literal curves. Curved alignment under soft soil is already tricky on land. Underwater, under pressure, it becomes a nightmare. Engineers had to design the tunnel rings with variable geometry so the alignment maintained its shape without warping. Every segment had to withstand uneven forces, constant vibration, and shifting water pressure without ever losing its seal. Local weather added another layer of chaos. Typhoons frequently hit the region, bringing waves that disturbed the seabed and shifted sediment patterns. A storm passing hundreds of kilometers away could still alter the ground pressure around the tunnel. Crews used a real-time marine monitoring system that tracked weather, tide height, and seabed shifts. If a typhoon was forming even before it touched land, tunneling operations would adjust torque and pressure settings to avoid sudden imbalances. But the Jintang project wasn't just a story of engineering guts. It was also one of coordination. Thousands of workers, dozens of marine platforms, and continuous supply routes had to be kept perfectly in sync. Sealants, concrete segments, steel reinforcements, and machinery parts were delivered like clockwork. If one shipment was late, the tunnel could lose crucial hours of controlled pressure, risking collapse. By the time the final lining was installed, Jintang had earned a reputation far beyond China. International engineering communities began referencing the project as a case study in managing soft soil undersea conditions. Even teams from Europe and the US, usually skeptical of China's rapid build style, took notice. They recognized the level of precision and hazard management required to pull this off. In the end, the Jintang undersea tunnel didn't just connect an island, it proved that China could tackle aggressive marine environments that many countries would avoid. It set a new benchmark for slurry shield tunneling and showed that if the terrain fought back, China would just engineer harder. And then came a tunnel that pushed both scale and ambition into an entirely new league: Shenzhen-Zhongshan Tunnel. The Shenzhen-Zhongshan Tunnel is the kind of project that makes even experienced engineers pause, blink twice, and say, "Hold on, they're doing what?" It's not just an undersea tunnel, it's part of one of the most ambitious cross-bay links ever imagined. Slicing through the turbulent waters of the Pearl River Delta, one of the busiest and most geologically complicated marine zones in Asia.
The project I've come to check out is known as the Shenzhen Link, which once completed will constitute a 24-kilometer major transit corridor between Shenzhen and Zhongshan.
The challenge here wasn't only the sea, it was everything under it, around it, and moving through it. The region is basically a perfect storm for engineering headaches. Soft seabed sediments, high seismic sensitivity, massive shipping routes, and currents that behave like they're trying to drag the whole ocean sideways. Any one of these issues could stall a tunnel project. Shenzhen-Zhongshan had all of them at once. So instead of relying on traditional methods, China went big, record-breaking big. They built the world's largest underwater immersed tube tunnel, stretching across deep water and connecting two of the country's most important economic hubs. And to make this happen, they didn't just use large tunnel elements. They created sections so big that each one looked like a floating building. Imagine a 180-meter-long steel tube, wide enough to carry 6 lanes of traffic, being dragged across a busy shipping lane while staying perfectly level. That was just a normal Tuesday on this project. Before the elements could even be placed, engineers had to deal with the seabed. The natural terrain wasn't level enough, so they reshaped it, like smoothing a giant underwater highway, using deep excavation, precision dredging, and seabed stabilization. Every centimeter mattered. If the seabed was off by even a few inches, an entire tunnel section could tilt, misalign, or fail to seal properly. Then came the immersion process, something tunnel builders around the world rarely attempt at this scale. Each massive tube was floated out, guided by tugboats, and slowly lowered into the prepared trench using synchronized winches and ballast systems. The placement had to be perfect. No sliding, no tilting, no drifting. Underwater divers and sensors monitored alignment in real time. Even waves from passing cargo ships had to be predicted so the crews could time each maneuver. Inside the tubes, the challenge shifted to pressure management. Parts of the tunnel sit more than 40 meters below the surface, meaning the structure must resist tremendous force. Engineers used a special composite lining system designed to flex slightly instead of cracking, kind of like a metal rib cage with a shock absorber built in. That flexibility, plus waterproofing layers and multi-level sealing systems, helped the tunnel withstand shifting seabed loads and the dynamic forces of the delta. Another major issue was ventilation. A long, deep underwater roadway tends to collect heat, exhaust, and humidity. The solution was a ventilation system inspired by subway airflow designs, with jet fans, high-capacity air ducts, and real-time sensors that adjust airflow depending on traffic volume. It's basically a giant underground lung that keeps drivers breathing easy. But perhaps the most mind-blowing part of the Shenzhen-Zhongshan project was how engineers designed it to survive the unexpected. The Pearl River Delta is vulnerable to typhoons, big ones. The tunnel's exterior was reinforced to handle extreme pressure fluctuations. Its approach structures were storm-hardened, and emergency protocols were built with the assumption that nature would throw its worst at any time. Foreign engineers who reviewed the project's technical brief were surprised, not because China built something huge, but because it managed such precision under such harsh conditions. American, European, and Japanese experts, who initially doubted the feasibility, eventually acknowledged that the project represented a leap in immersed tube technology, pushing boundaries that had been stable for decades. In the end, the Shenzhen-Zhongshan tunnel didn't just connect two cities. It redefined what's possible underwater. It proved that, with enough planning, tech, and stubbornness, even the wildest waters can be tamed. But China wasn't done, because next came a tunnel that went deeper than all of them. Qingdao Subway Undersea Tunnel. The Qingdao Subway Undersea Tunnel may not carry highways, but it carries something equally important. People stretching more than 5 kilometers beneath the Yellow Sea's coastal waters. This tunnel connects critical parts of Qingdao's urban subway network. Unlike long-distance undersea highways, subway tunnels face unique challenges: tight construction footprints, constant urban vibrations, and the need to keep trains running smoothly and safely. Engineers had to deal with a tricky seabed that combined soft silt, tidal movement, and man-made obstructions from harbor activity. Unlike highway tunnels, a subway tunnel can't rely on oversized tube segments. The alignment and internal clearance must be precise, leaving very little room for error. This meant every meter of excavation had to be monitored using high-precision sensors that tracked settlement, pressure, and water intrusion in real time. To achieve this, China employed shield tunneling machines with special waterproofing and pressure control systems. These TBMs were custom-built for the Qingdao project, equipped with advanced soil conditioning tools and automatic monitoring that could adjust cutter head rotation and slurry flow instantly. Essentially, the machines were self-correcting underwater surgeons, carefully carving out a path while keeping workers and structures above safe. Waterproofing wasn't the only concern. The tunnel's ventilation, lighting, and safety systems had to meet both deep water and urban subway standards simultaneously.
The installation of fans in roads, underground railways, or railway tunnels requires a high level of technical skills, as the conditions of fixing the line are different in each case.
High-capacity ventilation fans, emergency exits, and fire suppression systems were integrated into the design from the start. Every element was modeled digitally to ensure it would perform under maximum tidal pressure, train load, and earthquake scenarios. Qingdao's local authorities were also keen to minimize environmental disruption. Rather than disturbing marine ecosystems with traditional dredging, the team used precise excavation and segmented tunnel lining installation to reduce the impact on water flow and marine life. It was a small but significant part of China's growing awareness that mega projects can't ignore ecological responsibility. Perhaps the most impressive aspect of the Qingdao project wasn't the technology itself, but the speed and coordination. The construction timeline was ambitious, requiring continuous 24-hour shifts and flawless supply chain management. Every concrete segment, reinforcement bar, and TBM part had to arrive exactly on schedule. Even minor delays could have risked water pressure imbalances or misalignments. When the subway tunnel opened, it instantly became a model for urban undersea construction. Chinese engineers had demonstrated that even in dense urban environments, undersea tunnels could be built efficiently, safely, and reliably. International experts noted that the Qingdao subway tunnel combined urban subway precision with large-scale marine engineering, something that few other countries had successfully attempted. The project also signaled a shift in China's infrastructure approach. It wasn't just about linking distant cities anymore. The country was now confident enough to tackle urban undersea networks, a field previously dominated by Tokyo, London, and New York. With Qingdao, China showed it could handle both the sheer scale of ocean-spanning tunnels and the meticulous demands of urban underground transit. China may be rewriting the underwater rulebook, but it's not the only country pushing limits. Here's how the rest of the world stacks up. Similar tunnels and innovations around the world. While China has grabbed headlines with its 5,000-plus meter undersea marvels, other countries have quietly been developing their own underwater engineering feats. The United States, Japan, Europe, and the Middle East all have examples where ambition, ingenuity, and sometimes sheer necessity have forced engineers to think beyond conventional limits. In the US, undersea tunnels tend to be shorter but come with their own challenges. Take the Holland Tunnel under the Hudson River or the newer East River subway tunnels in New York. While these tunnels don't approach the scale of China's newest projects, the technical demands, managing river currents, soft riverbed sediments, and urban infrastructure above, require precision engineering, pressurized TBMS, and real-time monitoring, much like their Chinese counterparts. The difference is often regulatory. US projects move slower, not because the engineering isn't possible, but because of permitting, environmental review, and safety checks. Europe has long been a pioneer in undersea tunneling. The Channel Tunnel connecting the UK and France remains iconic, stretching 50 kilometers beneath the English Channel. It set records in the 90s for length and complexity, navigating chalk marl formations and high-pressure water zones. European engineers also innovated in safety. Continuous monitoring, ventilation, and emergency egress designs set the bar for modern tunnels worldwide. The Channel Tunnel influenced China's large-scale planning, especially in terms of redundancy and long-term operational reliability. Japan's tunnels, on the other hand, have focused on seismic resilience. The Seikan Tunnel, one of the world's deepest, slices through both soft seabeds and tectonically active zones. Japanese engineers developed advanced shield machines capable of withstanding underwater earthquakes and tsunamis, creating a model for risk management that has inspired international designs, including China's approach to typhoon-prone regions. Elsewhere, the Dubai Metro Undersea Extension and Istanbul's Marmaray Tunnel showcase innovative approaches in urban environments.
The only city in the world that straddles two continents. In the spring of 2004, a consortium of international engineers began work on the Marmaray Tunnel project.
Dubai combined artificial islands and immersed tube technology to connect key areas beneath the Persian Gulf, while Istanbul's project navigated one of the busiest shipping lanes in the world, requiring both precision placement of tunnel sections and real-time monitoring of seismic activity along the Bosporus. What's clear is that many nations are borrowing lessons from each other. China's advances in TBM automation, pressure balancing, and slurry shield design are now being studied internationally. Conversely, Europe's safety protocols and seismic planning are gradually influencing newer Chinese projects, creating a feedback loop of innovation. It's a global arms race of engineering, but one measured in concrete, steel, and water pressure, rather than missiles or tech. One unique trend is the hybrid approach, mixing immersed tube tunnels with shield board sections. This method allows builders to adapt to different seabed conditions along a single route, reducing risk while maximizing efficiency. Projects in South Korea, Singapore, and Norway have successfully tested hybrid methods, showing that modern undersea tunnels are no longer one-size-fits-all. Finally, technology integration has become universal. High-precision GPS alignment, AI-driven monitoring systems, and real-time pressure adjustment sensors are no longer exclusive to China. Every major tunnel project worldwide now uses some form of digital oversight, making underwater construction safer, faster, and more predictable than ever before. The takeaway? China may be leading in sheer scale and speed, but the rest of the world is innovating too. Each country has its own strengths: seismic resilience, urban integration, environmental mindfulness, or safety redundancies. Together, these projects are pushing global undersea tunneling to levels that were unimaginable just a few decades ago. With China raising the bar, the world is now in a race to see who can tunnel smarter, faster, and deeper. The underwater race. Who's next? The era of mega undersea tunnels is far from over. China's achievements have set a clear benchmark, but engineers and planners around the world are already thinking about what comes next. It's not just about connecting cities or islands anymore. It's about pushing the limits of technology, safety, and sustainability under the ocean. For starters, tunnel lengths are only going to grow. Experts predict that within the next decade, China and possibly other countries could attempt projects surpassing 10 kilometers underwater, linking major economic zones across bays, straits, and even small seas. To do this, TBMS will have to become smarter, with more automation, AI-assisted decision-making, and self-correcting cutter heads that can adapt to sudden geological changes without human intervention. Sensors will constantly monitor soil conditions, water pressure, and seismic activity in real time, reducing risk and boosting efficiency. Speed and cost efficiency will also dominate future designs. China's rapid construction pace has impressed the world, but other nations are experimenting with modular tunnel segments, prefabricated materials, and hybrid immersed bore designs that could reduce construction timelines without sacrificing safety. Drone-assisted inspection, robotic maintenance crews, and AI-driven logistics could make continuous underwater projects far more feasible than they were even a decade ago. Safety remains a universal concern. As tunnels grow longer and deeper, emergency systems will need to be revolutionary. Multi-level escape routes, pressurized emergency pods, automated fire suppression, and redundant ventilation systems will become standard.
Ventilation is critical, particularly with road tunnels where high levels of pollutants, including carbon monoxide and nitrogen oxide, are continually discharged.
Engineers are also exploring materials that can flex without cracking under immense underwater pressure, giving tunnels the resilience to survive earthquakes, storms, or unexpected seabed shifts. Environmental impact is another critical focus. Modern undersea tunneling cannot ignore the ocean ecosystem. Future projects will integrate real-time monitoring of marine life, sediment displacement, and water quality. Construction methods will continue to evolve toward minimal seabed disruption, including more precise dredging, jet grouting, and environmentally friendly slurry management. Lessons from Europe, Singapore, and Japan are helping Chinese engineers balance ambition with conservation. The global implications extend beyond engineering. These tunnels are catalysts for regional economies, tourism, trade, and urban planning. Imagine a network of mega-tunnels connecting island cities in Southeast Asia, linking ports across the Gulf of Mexico, or providing fast commuter lines between Europe's island and coastal hubs. Faster transit translates to economic efficiency, urban growth, and even geopolitical influence. Countries that master undersea tunneling can control trade routes and mobility like never before. Finally, collaboration is on the horizon. China's methods are being studied in America, Japan, and Europe, while Chinese engineers are learning from seismic innovations in Japan and safety protocols in Europe. The next wave of projects is likely to combine the best of global experience, speed and scale from China, earthquake resilience from Japan, and safety redundancy from Europe. The result? Undersea tunnels that are longer, deeper, safer, and more environmentally conscious than any that exist today. The takeaway is clear. China started the mega-tunnel revolution, but the race is global. Over the next decade, expect tunnels that feel almost science-fictional, massive steel and concrete arteries moving people and goods beneath the ocean faster, safer, and smarter than anyone thought possible. China's global tunneling collaborations. When people think of China's undersea tunnels, they usually picture massive projects like Shenzhen-Zhongshan or Zhanjiang Bay. But what's less talked about is how China is sharing this expertise beyond its borders. Engineers, researchers, and construction firms from around the world are now studying, adopting, and even collaborating with Chinese teams to tackle projects that were previously thought impossible. One major area of influence is technical consultancy. Chinese firms have been invited to advise on undersea projects in Southeast Asia, the Middle East, and even parts of Europe. Their input isn't just about throwing massive machines at a problem, it's about sharing practical knowledge. How to handle high-pressure seabeds, maintain shield-boring machines for long stretches, and manage massive material supply chains with military-like precision. Countries facing soft soil challenges, frequent typhoons, or seismic activity have found China's experience invaluable. Beyond consultancy, China has been actively involved in joint ventures. For example, Southeast Asian nations have partnered with Chinese construction companies to build medium-scale undersea links, combining local labor knowledge with Chinese technical innovations. These partnerships often include training local engineers, installing monitoring systems, and transferring machine technology so the projects remain sustainable long after construction is completed. It's a mutually beneficial model. Host countries gain advanced tunneling expertise, while Chinese firms expand their international footprint. China also contributes heavily to research and development collaboration. Universities and engineering institutes around the world have entered cooperative programs with Chinese counterparts, focusing on soil mechanics, pressure-resistant tunnel linings, and real-time monitoring systems. These R&D initiatives aren't just academic. They feed directly into real-world projects, making tunnels safer, faster, and more efficient globally. For instance, lessons learned from the Shenzhen-Zhongshan tunnel's curved alignment and high-pressure management have informed studies in Japan and Europe for both highways and subway tunnels. In addition, China's technology is helping modernize existing tunnels abroad. From sensor networks to automated slurry shield management, retrofitting old undersea tunnels with Chinese-style innovations is becoming more common. Engineers in places like the Middle East, where harsh desert-to-sea projects are increasingly needed, have found China's approach to materials, precision alignment, and pressure balancing particularly useful. Perhaps the most significant impact is cultural. China's emphasis on speed, precision, and large-scale coordination has inspired international engineering communities to rethink what's possible. Where many projects abroad still treat long, undersea tunnels as high-risk ventures, requiring decades of planning, Chinese methods demonstrate that careful planning, advanced technology, and continuous monitoring can safely accelerate construction timelines. China isn't building tunnels in isolation. Its influence is spreading globally through training, joint ventures, R&D partnerships, and technological exports. The result? A new generation of undersea projects worldwide that are smarter, faster, and more resilient than anything attempted a few decades ago. In many ways, China has become the hub of modern tunneling know-how, transforming not just its own cities, but the possibilities for engineers everywhere. China's undersea tunnel projects have redefined what's possible beneath the waves. From massive domestic megaprojects to global collaborations, their technology, precision, and speed are influencing engineers worldwide. As nations adopt these innovations, tunnels are becoming longer, safer, and more efficient. The era of underwater mega-engineering is here, and China is leading the charge. That's a wrap on the world of China's undersea tunnel marvels, engineering at its boldest and most ambitious. Don't miss out on more incredible tech stories. Hit subscribe and stay tuned for our next deep dive.